Hi, morning class.
Good morning, Lord.
Okay.
Morning, Lord.
Good morning, Laushi. Good morning.
Good morning, 老师.
Last class, we have learned the types of stress and their safety factors. Now, let's review the content of last class. Okay, the classification of alternating stresses. Alternating stresses includes cyclic stress and random stress. The cyclic stress changes periodically with time, and for random stress, the applied loads vary irregularly in their amplitude. There are 5 parameters to characterize stress variations: the maximum stress, the minimum stress, mean stress, stress amplitude, and stress ratio. The mean stress is the average of the sum of maximum stress and the minimum stress. The stress amplitude is half of the stress rate, and the stress ratio, R, is the ratio of the minimum stress to the maximum stress. Like this. And we also studied 4 special stress cases. When the stress ratio R is -1, the stress is completely reversed stress, like this. And when the stress ratio R is 0, it's repeated stress. And when the stress ratio R is 1, it's static stress. The stress is constant. And for the fluctuating stress, it is an alternating stress with a non-zero mean value, and the stress ratio is greater than -1 and less than 1. It can be regarded as the superposition of a completely reversed stress on a static stress. And for the static stress, the maximum stress is equal to the minimum stress, and the stress ratio is 1, and the mean stress is equal to the maximum stress. The stress amplitude is 0. And for the fluctuating stress, we have this. And for completely reversed stress, the stress ratio is -1, the mean stress is 0, and the stress amplitude is equal to the maximum stress. And for repeated stress, the minimum stress is 0, so the stress ratio is 0, and the mean stress is equal to the stress amplitude. It's half of the maximum stress. The stress The suggestion criteria for static stress can be expressed as the maximum working stress should be less than the allowable stress. This is the allowable stress, and the allowable stress is determined by material stress limit divided by an allowable safety factor. Designers must ensure the maximum stresses are less than the material stress by a sufficient margin to guarantee adequate safety for an element, and the margin is the safety factor. The safety factor is determined by the stress limit divided by the maximum working stress, and the calculated or designed safety factor should larger than the allowable safety factor. And for ductile materials, we choose yield stress as the stress limit. And for brighter materials, we choose sigma B as the stress limit. But for alternating stress, the element may failure under a low load, uniformly much less than yield stress because of fatigue. So the yield stress and ultimate stress sigma B cannot be used as stress limit to obtain safety factor. We need to define a new stress limit. Before that, we need to understand the vertical fracture. The vertical fracture failures occur at relatively low loads, and there are three typical zones of vertical fracture: the correct origin zone, beach marks zone, and sudden fracture zone. The beach marks zone corresponds to the vertical crack propagation. We use stress life diagram to describe the stress limit or the endurance strength of materials at different numbers of cycles under the same stress ratio. For this, it's under the stress ratio R. The stress life curve can be split into 4 stages. Stage AB can be regarded as a static stress state. And stage BC, the number of cycles is less than the third power of 10. It's low cycle stage. And beyond point D, it's an infinite life stage. The material can withstand load without failure. The number of cycles is infinite. The stress is called the vertical limit or endurance limit sigma R infinite. is the endurance limit for infinite life. Since the number of cycles and since the number of cycles ND is quite large, a critical number and their rule is selected. Uniformly, and their rule is the 7th power of 10. The corresponding vertical limit at N0 is sigma R. R is stress ratio. For stage say D, the number of cycles is less than the critical number of cycles N0 and large than the third power of 10. The corresponding endurance limit at the number of cycle n is sigma r n instead of sigma r. Sigma r is the endurance limit for infinite life, and the corresponding number of cycles is n0. And for sigma r n, the number of cycles is n, and n is greater than the third power of 10 and less than the n0. And for stage CD, we have this. The m's power of sigma Rn times n is constant. When the stress ratio R is -1, we have this. The m's power of sigma -1m times n is constant. Then the stress criterion for material under cycle stress can be expressed as this. The safety factor the safety factor is determined by the endurance limit sigma -1n divided by the maximum stress, and it should larger than the allowable safety factor. So sigma -1n is the stress limit. When the material is subject to a completely reversed stress and the number of cycles is finite. From stress life diagram, we can obtain endurance stress or stress limit when the number of cycles is greater than the third power of 10 and less than the n0. When the number of cycles is infinite, the number of cycles is larger than n0. we use sigma R as endurance stress or stress limit. We have endurance limit diagram to obtain sigma R. The difference between stress life curve and the endurance limit diagram are: first, the stress life curve represents the endurance stress of materials of different number of cycles under the same stress ratio. But the endurance limit diagram is used to evaluate vertical limit or endurance stress of materials for the same life. Usually, then the numbers of cycles is N0 under different stress ratio. And second, the stress life curve is used to obtain the endurance stress sigma Rn under finite life. But the endurance limit diagram is used to evaluate endurance stress sigma R under zero, under N0 or infinite life. For the endurance limit diagram, there are several important points. Point A represents the endurance limit of completely reversed stress, sigma -1. And point B there represents the ultimate stress, sigma B. Point C represents endurance limit of repeated stress, sigma 0, not sigma -1, sigma 0. And point E is the yield stress. Points on the horizontal axis represent a static stress state with the stress ratio R is 1, and points on the vertical axis represent a completely reversed stress state that is R is -1. Life EF represents the stress state where the endurance limit is the same as the yield stress. Points in zone A, F, E, O indicate safety. Points outside zone A, F, E, O indicate failure. And points on line A, F, E indicate endurance limit. The stress limit points on line A, F, E. In this zone, the material is safe. And the actual endurance limit of a meshing element will then be 0. And for the meshing element, how to find its stress limit or endurance stress. We consider it in 3 pieces. When the stress ratio R is constant, then we connect the origin O and point M and extend the line to intersect with the endurance limit A1, F1 at point M1, and then we can find the coordination of intersection point M1. Then we have this. We use the calculated safety factor. It's determined by this. We use this to calculate the safety factor. And we should consider the static stress. Okay. And if the line ON extend the line ON to intersect EF at point M1, we use this to calculate the safety factor. And when the mean stress is constant, we can use this to find the endurance stress, and points on vertical lines through the working point M, that is MM2, represent the same mean stress. And the vertical stress for constant mean stress is this. We use this to calculate the safety factor. And if the point, for the point N, the point N2 is the endurance stress, and then the safety factor is determined by this. And if the minimal stress is constant, the point M3 is the endurance stress for the point M. We also can find the coordination of the intersection point M3 and vertical stress for constant minimal stress is expressed as this. We use this to calculate the safety factor. And for point N, the point N3 is the endurance limit. We use this to calculate the safety factor. Okay, this is the practice last class. So let we see this practice. An element has a maximum stress. The maximum stress is 300, and the minimum stress is minus 50 megapascal. And the yield stress is 850 And the endurance limit sigma minus 1 is 500. And the endurance limit sigma 0 is 800. This is the endurance stress when stress ratio R is minus 1. And this is the endurance stress when stress ratio R is 0. And push sigma is 0.25. And the K sigma is 2. And the stress ratio R is constant. If the allowable safety factor is 1.5, draw a simplified sigma M sigma A diagram of the element and determine whether the element will meet the stress requirement. Okay. First, calculate stress amplitude and mean stress. We use this equation to calculate the mean stress. The mean stress is 125. And we also can calculate the stress amplitude. And the stress amplitude is 175. We have noted that the yield stress, the endurance limit sigma minus 1, and the endurance stress sigma 0. Then we can draw a simplified sigma M sigma A diagram. For the point, this is the curve. Point A is sigma minus 1. C is sigma 0. E is sigma S. We have looked at the sigma S, sigma minus 1, and sigma 0. So the coordination of point A is 0 sigma minus 1. And the coordination of point C is half of sigma 0 and half of sigma 0. And the coordination for point E is sigma S 0. And then we can obtain this. This is the coordination for point A, and this is the coordination for point C, and this is the coordination for point E. And the line equation for EF can be expressed as sigma A plus sigma M is equal to sigma S. Sigma S is 850. We can obtain this line equation, and then we can draw this line. And the line equation for AF can be expressed as sigma minus 1 is equal to sigma A plus push sigma times sigma M. And we know that the value of sigma minus 1 and push sigma minus 1 is 500 and push sigma is 0.25. Then we can draw the line AF and obtain the simplified sigma A, sigma M diagram. And then calculate vertical stress safety factor by infinite life. Infinite life. Okay. Oh, this. Because the stress ratio is constant. So we use this equation to calculate the safety factor. The sigma minus 1 divided by K sigma times sigma A plus push sigma times sigma M. Sigma A is stress amplitude. Sigma M is the mean stress. We have calculated that the sigma A, the stress amplitude is 175 and the mean stress is 125. And the endurance limit sigma minus 1 is 500. K sigma is 2, push sigma is 0.25. So we calculate the safety factor is 1.31. But the allowable stress from the below that the allowable safety factor is 1.5. So the calculated safety factor is less than the allowable stress. So the element is not safe when it's under infinite life. It's not safe because the calculated safety factor is less than the allowable safety factor. Okay. And this is a summary of safety factors under several stress states of stable cyclic stress or with uniform stress amplitude. This is for static stress. This is for the static stress. When the material or element is subject to a static stress, we use this. Then we can calculate the allowable stress, and the working stress should less than the allowable stress. And we use sigma S or sigma B as the stress limit. When the material is ductile, we use sigma S. When the material is brighter, we use sigma B. And this is for the cyclic stress when stress ratio R is constant. And we use this to calculate the safety factor, but we also should consider the static state. This is for the static state because under the cyclic stress, this means under the cyclic stress, the R is C, the material or the element is thinner because of yielding, not vertical. This is for vertical, and this is for yielding. And when the mean stress is constant, we use this to calculate the safety factor for vertical, and use this to calculate the safety factor for yielding. And when the minimum stress is constant, use this to calculate the safety factor for vertical and this for yielding. So this is a summary of safety factors under several stress states. And this cyclic stress have uniform stress amplitude like this. The stress amplitude is uniform. It's uniform. But in real engineering practice, nearly all meshing elements are subject to unstable stress like this. The variations in stress amplitudes make the direct use of standard stress life curve inapplicable because these curves are developed from constant stress amplitude. So it becomes necessary to develop a verified theory to predict vertical stress for unstable stress. And and now let's have a break, okay? Have a break for 20 minutes, okay?
Yeah, okay, Lucy. Okay.
Okay. Okay, let's continue. And we have looked at the safety factor for static stress and the condition. The R is constant, the mean stress is constant, or minimum stress is constant. To calculate the safety factor, this is for vertical, and this is for yielding. This is for yielding, okay? And in this exercise, if the condition is not, the stress ratio is constant. The condition is the mean stress is constant, or the minimum stress is constant. We should use this equation or this equation to calculate the safety factor. Okay, and and then we consider the situation when the stress is unstable. And for this, and the changes of the amplitude is regularly, like this and this. For the regularly unstable stress, we use this theory to obtain vertical stress, and the rule assumes that any stress amplitude greater than the endurance limit greater than the endurance limit contributes certain vertical damage to the element, and the amount of damage depends on the number of cycles at that stress amplitude and the total number of cycles that would produce failure to a standard specimen at the same stress amplitude. And when the total accumulated damage generated by different stress levels reaches a critical value, vertical failure occurs. And this is the assumes for this ruler. And we have assumed that sigma 1, sigma 2, sigma 3, and sigma I are the maximum stress of each cycle. The maximum stress for each cycle. And and the lowercase n represent the number of cycles. N1, N2, N3, and I are the number of cycles acting on the element at each stress level sigma I. For this, N1 is the actual number of cycles acting on the element at sigma 1. And the uppercase N represents the number of cycles to failure at each stress level sigma I obtained from the stress life curve. Okay, for sigma 1 is the maximum stress of this, the maximum stress, and the corresponding number of cycles to failure is the uppercase N1, and the actual number of cycles acting on the element is the lowercase N1. Okay. And then for stress greater than the endurance limit, each cycle will cause certain damage, and the damage contribution of N1 cycle at stress 1 is assumed to be the lowercase n1 divided by the uppercase n1. The lowercase n1 is the actual number of cycles, and the uppercase n1 is the number of cycles to failure. This is the actual number of cycles, and this is the number of cycles to failure for sigma 1. And where the damage contribution of N2 cycles at stress 2 is assumed to be this. Similarly, the damage caused by Ni cycles at stress sigma I, not sigma 1, it's sigma I, is this. So when the cumulative damage approach 1, vertical failure ensues, and the inner cumulative vertical damage ruler can be expressed as this. The lowercase ni divided by uppercase ni, the sum of this is 1. Okay, or the summation of ni divided by ni is 1. Okay. For the stress life curve, we have this. The m's power of sigma I times ni is constant for the stage CD. Okay, it's from the stress life curve. We have this equation. And therefore, we can calculate Ni. Ni is the number of cycles to failure under the sigma I. We can use this to calculate Ni. And we also have this from the assume the summation of this is 1. Means the cumulative damage approaches 1, and then the vertical failure ensures. Then we can obtain this. Okay, we can obtain this. The summation of Ni times the m's power of sigma I is equal to N0 times the m's power of sigma minus 1. Okay. Sigma minus 1 is the endurance stress when the stress ratio is minus 1, and N0 is the corresponding corresponding number of cycles to failure under this stress. Okay, so we have this equation, and assume that the vertical effect of variable amplitude stress is equivalent to that of a constant amplitude stress sigma v. Uniformly select sigma v as sigma 1 that operates the equivalent number of cycles and v. Then we have this. The summation of n(i) times the nth power of sigma I is equal to nv times the nth power of sigma v, and sigma v has a constant amplitude stress. Okay, and then the equivalent number of cycles nv is then derived as this. Okay, sorry, wait a minute. Okay, let's continue. And then the equivalent number of cycles nv can expressed as this, or I can use this to calculate the nv. nv is the equivalent number of cycles, and then the corresponding to the equivalent number of cycles nv, the endurance stress for completely reverse stress sigma -1 nv can be expressed as this. So we can use this to calculate the endurance stress for completely reversed stress sigma -1 nv. Then the safety factor of the element under variable actual stresses is this. The calculated safety factor is determined by the stress limit divided by the maximum stress, and is equal to the sigma -1 nv over sigma 1, and can expressed as this, and should larger than the allowable safety factor. Or I can use this, use sigma -1 divided by the calculated stress should larger than the allowable stress, and the calculated stress can be expressed as this. So this and this is the same. And let's say the example. A rotor shaft has vertical properties of endurance limit sigma -1. It's 300 megapascal, and the material constant m is line. The number of critical cycles n0 is the surface power of 10, and this is for the stresses with constant amplitude. Okay. In the wise, the shaft is to be subject to a spectrum of completely reversed stress. First, 500 megapascal for the first power of 10 cycles. Then 400 megapascal for the fifth power of 10 cycles. After this loading sequence has been imposed, it is desired to change the stress to 350 megapascal. Estimate the remaining cycles for the shaft at the final stress level if the duty cycle is to be repeated 4 times during the life of the shaft. Okay, and this is the shaft is subject to a unstable stress. Okay, and then we have this to calculate the Ni. Okay, Ni. We have this N1. N1 is the number of cycles to failure under sigma 1. Okay, under sigma 1. So it's equal to N0 times the nth power of sigma minus 1 or sigma 1. We lose the value of N0 is the 7th power of 10, and sigma minus 1 is 300, and sigma 1 first stress or fourth cycle, the stress is 500. Then we can obtain the numbers of cycles to failure under sigma 1 means this N1, the number of cycles to failure under sigma 1. We can obtain this N1, okay? and similarly, we can calculate N2, the number of cycles to failure under sigma 2, okay? And sigma 2 is 400. And then calculate N3, the number of cycles to failure under sigma 3. Sigma 3 is 350 megapascal. And calculate N3. And then we have N1 over N1 plus N2 over N2 plus N3 over N3 is 1. This is the number of cycles to failure, and this is the actual number of cycles. Okay, and in this example, it should be repeated 4 times. 4 times. So we have 4 times this is 1. And for sigma 1, we know that the lowercase ni is actual number of cycles is the first power of 10. And N2 is the fifth power of 10. So then we should calculate the N3. and use this. Therefore, we calculate N3 is 4.21 times the first power of 10. So if the shaft want to repeat it 4 times during the life, so the remaining cycles for sigma 3, the 350 megapascal, the remaining cycles is this. The N3 is this. Calculate this, okay? And for this example, a 45 steel element is to be subject to a spectrum of completely reversed stress. It will be cycled at 500 megapascal for the first power of 10 cycles. Then the stress will be changed to 400 megapascal for the fifth power of 10 cycles. We know that the sigma minus 1 is 300, m is 9, and the n0 is 5 times the 6th power of 10. First, calculate the safety factor. So we should use which equation to calculate the safety factor? Which equation? And then after this loading sequence has been imposed, the stress will be changed to 350 megapascal. Calculate the number of cycles before it breaks. So first we should calculate the safety factor. Okay, for the stress with unstable stress with unstable amplitude, how to calculate its safety factor? We use this, okay? We use an equivalent sigma, equivalent numbers and stress to calculate the safety factor. And for this equivalent sigma minus 1 and V, the stress amplitude is constant. Okay, for this, the stress amplitude is constant. And how to calculate this? We use this to calculate. And this is the sigma minus 1. For sigma minus 1, we know that. And this is the material constant. And we know the N0. And this is the summation of Ni times the nth power of sigma I. And this is for the, this is the stress, unstable stress. Okay, unstable stress. And so first, calculate the safety factor. We can calculate Ks is this. Then calculate the safety factor, or we can use this. It's the same. It's the same. This equation and this equation is the same. We use this equation to calculate safety factor for the unstable stress amplitude stress. Okay, and we know that the value of sigma minus 1, value of m and n0 and ni and sigma I, okay? n1 is the first power of 10, and the sigma 1 is 500. N2 is fifth power of 10, and sigma 2 is 400. And then we calculate the safety factor is 1.14. 1.14. Sorry. Okay. Sorry, wait a minute. Okay, sorry, let's continue. And we calculate the safety factor. And then second, calculate the number of cycles to failure at each stress level. Okay, for sigma 1 is 500 megapascal. The number of cycles to failure, N1, we use this to calculate. And similarly, we calculate N2 and N3. Okay, this is the number of cycles under sigma 1, sigma 2, and sigma 3. And from this ruler, we have this. Okay, so we use this to calculate the N3, to calculate the number of cycles before it breaks under sigma 3, 350 megapascal to calculate this. So we use this to calculate this. This is for N1 for sigma 1, and this is for sigma 2, and this is for sigma 3. And then the number of cycles before it breaks, the N3 is this, 0.97 times the 6th power of 10, okay? Okay, so any questions for the two examples? Any question? It's to calculate the safety factor of
Lastly,
unstable
can you just give like a little explanation on the calculation of the safety factor again? It's a little
wait,
complicated.
example 5.
Yes.
Okay, sorry, wait a minute.
Okay.
Okay, let's continue. Okay, for the
Okay, Laoshi.
example 5, we know that the low condition is sigma -1, the m, and the n0, and we know the sigma 1, 500, and this is the n1. Okay, n1 is the actual number of cycles, and the sigma 2, n2, and the sigma 3. Sigma 3, okay? And then we should calculate the n3, okay? n3, the number of cycles under sigma 3 before each failure, and for this stress sequence, it should be repeated 4 times during the life. Okay, 4 times during the life. Okay, so first we calculate the number of cycles to failure. Any problem? Any problem? To calculate the number of cycles to failure under sigma I.
Laoshi, no problem. So Laoshi,
No
the n0 is the number of critical cycle. The n0.
N0.
Yeah.
N0 is the number of critical cycle under stable
Okay.
stress.
Under stable condition. Okay. Then ni is the
Ni is the number of cycles to failure under each stress level. Under each stress level.
And the sigma 1 and sigma I are the 500 megapart and the 400 megapart. Okay.
Okay, and we can see this finger. Okay, there. For sigma 1.
Okay, Laoshi.
Okay, sigma 1.
Yes.
If the stress is stable, it's sigma 1. Okay, the stress is stable, and the critical number of cycles is n1. But the stress is unstable. It can change sigma 1, sigma 2, sigma 3, sigma 4. Okay, so n0 can't used to be the critical number of cycles. Okay.
Laoshi, can you send the PPT to the group? Okay, please.
Okay. No problem. And calculate the ni and use this ruler to calculate the n3. It repeated 4 times. 4 times this is 0. Therefore, calculate the n3. Okay. Any problem?
Okay, Laoshi. No problem.
Okay. No problem. Okay. Okay. Let's continue. Okay, this is the example 6, and then they had a practice. An element is subject to a spectrum of completely reverse stress, and first 500 for this sigma 1 and 1, and then 456 sigma 2. Okay. And n2, and this is sigma 3, 400 megapascal for 3 times the 6th power of 10. So we know sigma 1, sigma 2, sigma 3, and the lower case n1, n2, and n3. After this loading sequence has been imposed, the specimen is damaged. If the element is to be subject to a stable amplitude stress, okay, the stress is 500 megapascal. Estimate the number of cycles to failure n, and the number of cycles to failure n is under the stable amplitude stress. Okay. So you should.
Okay, Lash.
So you have 10 minutes to consider and discuss how to do this exercise. Okay. I have 10 minutes.
Okay, Lash. Okay, Lash.
Okay. Okay. Calculate by yourself. Okay.
Lashi, I don't have the formulas because I don't have the PPT. Lashi, can you send the PPT now, please?
Okay, I send it now. Okay.
Okay, thank you, thank you. Lashi, I can't see the question again. Lashi, I can't see the question anymore.
Wait a minute. Wait a minute.
Okay, Lashi.
So can you see the PPT now?
Yes, Lashi. Yes, Lashi.
Okay,
Can
okay.
see.
Okay. You have 10 minutes to calculate. Okay.
Yes, Lashi. Yes, Lashi. I
Okay. Have you finished the calculate? Finish the calculating? Any problem for this exercise?
Yes, yes, Laoshi. I have one question, please.
Also for
Oh.
me.
Okay. Let's
Um,
say the calculation process. Okay. And
Okay,
we
okay.
know the unstable stress sigma 1, sigma 2, and sigma 3. And then we also know the actual numbers of cycle N1, N2, and N3. Okay. And then we should estimate the equivalent number of cycles N. The equivalent number of cycles N. And the number of cycles N is under stable amplitude stress. Okay. 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 Noisy. Then the number of cycles acting on the element at each stress level, they have for sigma 1. For sigma 1, N1 is 2 times the 6 power of 10. And for sigma 2, the N2 is the 6 power of 10. And for sigma 3, N3 is 3 times the 6 power of 10. Okay, we know that. And then determine the equivalent number of cycles NV under a constant amplitude stress sigma V. We have this equation. Okay, this is the summation of Ni times the nth power of sigma I, and this is for the unstable stress. And mv times at the nth power of sigma v, this is for the stable stress. Any question for this equation? For this equation. Okay, of course, in to obtain the safety factor of unstable stress, we assumed constant amplitude stress and to calculation and and use this, and we have this ruler. Okay, for the 3 cycles, the element is damaged, and then the MV can calculated by this. We have row N1, okay? N1 and sigma 1. Sigma 1 is the first cycle of the unstable stress, and this sigma 1 is the stable stress. Okay, the stable stress is 500, and plus the N2 times sigma 2 over sigma 1, and times the N3, and plus N3 times this. Okay, this is sigma 1, sigma 2, and sigma 3 is unstable stress levels. And this is for the stable stress. And then for M is 9, then we calculate MV is 2.79 times the nth power, the 6th power of 10. Any problem? Any problem?
I think no,
Yes,
老师。
Oh,
老师。
for this calculation? Any problem?
老师，the M
Uh,
the M equals 9. M
M
equal to 9.
M
Yes.
M
Yes, Lashi.
is materials constant. Universally, M
Constant.
is 9.
Okay.
Universally,
So
we said that
Lashi,
M is 9.
you
Okay.
give us M if you give us the question.
I should give you the value of M.
M in the question all the time.
Okay. Okay.
Okay. Thank you, Lashi. Thank you. I was a little confused, but now I'm okay. Okay. Thank you.
Okay. Okay.
All right.
Continue. The
Yes,
second
please.
exercise. An element is subject to a spectrum of completely reverse stress. It will be cycled at sigma 1, 500 megapascal for the first power of 10 cycles. Then the stress will be changed to 400 megapascal for the fifth power of cycles. And finally, the stress will be changed to 200 megapascal for the 6th power of 10 cycles. We know that sigma minus 1 is 300 megapascal. The material constant M is 9, and N0 is 5 times the 6th power of 10. Then calculate the safety factor. So we should calculate the safety factor under unstable stresses. Okay. You do it by yourself first. Okay.
Okay, Lashi. Okay, Lashi.
10 minutes. Okay.
Okay, Lashi.
Okay. Okay, have you finished it? Have you finished it?
Laoshi, yeah, still on it, but Laoshi, we can discuss it, no problem.
Oh, no problem.
Yes, Laoshi.
Laoshi, can you
No.
go through the processes, like just go through the steps?
Okay, let's see how to calculate. Okay,
Okay, Laoshi,
and
okay, Laoshi.
and we use this equation to calculate the safety factor. Okay, and we have law sigma 1, sigma 2, sigma 3, and n1, n2, n3. And we also learn sigma minus 1 and the material constant m and n0. Okay. All of this we have law. The sigma minus 1 m and 0 n I and sigma I. Okay. So we calculate the safety factor. Use this. We have the sigma minus 1 is 300, m is 9, and n0 is 5 times the 6 power of 10, and there is ni times the last power of sigma I plus n2 times the last power of sigma 2. There is low n3, sigma 3. Okay?
Mm-hmm.
We needn't consider sigma 3. Why? We needn't consider sigma 3. There is low sigma 3. Why?
Laoshi, because the
Than sigma minus 1.
Because
Laoshi,
what?
because the workpiece doesn't break.
Oh, no. They say that. Okay. Because why we needn't consider the contribution of sigma 3 because the sigma 3 is less than the endurance stress. The endurance stress sigma minus 1 is 300.
Yes.
Okay?
Mm.
We can say the okay, where? There. For the ruler, we assume that any stress amplitude greater than the endurance limit contributes certain vertical damage to the element should greater than the endurance limit. If the stress amplitude is less than the endurance limit, the contribution is very, very small. So we need to consider. Okay?
Yes.
Okay?
Okay, Laoshi, okay.
Okay? So in this practice, there we consider sigma 1 and sigma 2 because the stress amplitude is large. But for sigma 3, it's small. We needn't consider. You also can plus n3 times the last power of n3, but the calculated the result is very, very small. It's very, very small. Okay. So we use this to calculate the safety factor, and then the answer is 1.089. This is the safety factor for the unstable stress. Okay, and then this is the safety factor for unstable stress. Now we have low the safety factors for several stable stress and unstable stress, which the amplitude changes regularly. And then we have these stresses. Okay, it's easy to confuse about this. Now let me see the sigma s. The sigma s is the stress limit for ductile material. Okay, but for sigma b, in which condition we choose sigma b as stress limit? In which condition? In which condition we choose sigma b?
Laoshi,
Yeah.
when the fatigue limits under finite life n.
Oh, no. Sigma S is the stress limit for ductile material, and sigma B is stress limit
Oh shit.
for brighter material. For example, the cast iron. The cast iron is brighter. So for cast iron, we choose sigma B as the stress limit to calculate the safety factor. Okay. For steel, we can choose sigma S, the yield stress, to calculate the safety factor. But for sigma -1, in which condition we choose sigma -1 as stress limit? Sigma -1.
When the element fatigue limits under complete reverse stress at n0.
This
No, the third one. Yes, the second one. Completely
second one.
reversed. Yes.
Yes. Is the we choose sigma -1 as vertical limit under completely reversed stress and n0. Okay, for sigma r.
Laoshi, when it's completely reversed under the third one.
Which one? For sigma r,
Laoshi,
which one?
fatigue limits under infinite life with R, the last one. Yes.
This. Yes. The vertical limit on the infinite life with the stress ratio is R. Okay, for sigma r n, we choose which?
The first one. Fatigue limits under finite life.
Correct. First one. And for sigma -1 e.
Laoshi, the third one.
The third one.
Yes.
Yes, the element's vertical limit on the completely reversed stress at n0. And for sigma -1 n v.
Laoshi, the last one.
Yes, the last one. The last one is the equivalent endurance stress for unstable stress. Okay. So, for example, we use the strength criterion. The safety factor is determined by the stress limit divided by the maximum working stress. So if a steel shaft is subjected to static axial tensile stress, we choose which as the stress limit. We choose which as its stress limit to calculate the safety factor.
老
Choose which?
first one, the first one.
First
QS.
one, sigma s, the yield stress. Okay, correct.
Yes.
And then a cast iron shaft is subjected to static axial tensile stress. We choose
Now
which
the
one?
second one because cast iron is brittle.
Yes, it's okay. Yes, the second one. Okay, if a specimen carries a fluctuating stress and the number of cycles to failure is n and n is greater than that and less than that, we choose which one as its stress limit. Choose which one?
Actually, the third one because it's completely reversed since 10 exponent 3 is less than n and it's less than 10 exponent minus 10 exponent 7.
The third one?
Yes.
Okay. You should notice that the number of cycle n is finite, not infinite.
Actually, the fourth one.
Use this. Okay? Use this.
Okay, Lashi, okay.
And the sigma Rn can be obtained from the stress life diagram from the stage CD. Okay? From the stage CD. It's for the finite life. Okay? And a specimen carries a fluctuating stress and the number of cycles to failure is n0. So we choose which one? Choose which one? For this condition, we choose which one as
Lashi, the fourth one.
the first one, sigma
QR, yes. Yes.
R. Yes, it's for the infinite life. Okay, the stress limit for infinite life under fluctuating stress. Okay, and then a specimen carries a completely reversed stress and the number of cycles to failure is n0. We choose which one?
Lashi, the third one, completely reversed. And the number of
Yes,
cycles to failure
yes.
is n0.
Yes, we choose sigma minus 1 as the stress limit. Okay, and then an element, n element carries a completely reversed stress and the number of cycles to failure is n0. We choose which one? We choose which one?
Q minus 1e.
Yes, we choose this. Okay, and for the condition subject to an unstable stress, we choose an equivalent endurance stress. We choose this one. Okay.
Yes.
You choose this one. Okay. Now, this is under the situation. The stress is uniaxial stress. But when the stress is combined stress. Is combined stress. How to calculate a safety factor, okay? And then the static strength for combined stresses. And from the strength criteria, we have this, okay? And from the fourth strength theory or third strength theory, we have this. The sigma, the stress can use this to calculate. And this is for shear stress, okay? This is for shear stress, tau. And we use this to calculate the combined stress. And this calculated stress should less than the allowable stress. Use this or this. And this is for static stress state. And for the combined stress with constant amplitude, like this, we have this equation, and the safety factor should can express as this, S sigma times S tau and divided by the square root of S sigma square plus S tau square, and sigma S sigma and X tau can be expressed as this and this. We use this equation to calculate safety factor under combined stress with constant amplitude. Okay, and
Laoshi, please, is there another break?
have a break.
Yeah,
You
we had
want
only
to-
one break today.
Have a break.
Yeah, is there? I'm asking if there's another break.
Sorry, I can't hear you.
I'm asking if there's another break.
Have a break for you means have a break for 20 minutes.
Yeah, yes, Laoshi.
Okay, have a break.
Oh, sure, Laoshi.
Now let's continue. And this is to calculate the safety factor under the combined stress with constant amplitude. And for this part, we only need to have a basic understanding. If you are interested, you can see the examples in your book by yourself. Okay, page, let me see. Page 47, the example 2.2 is how to calculate the safety factor under combined stress with constant amplitude. Okay, so for the summary of the safety factor, we have this. This is for special stable cyclic stress, and this is for unstable stress. And for combined stress, this is for the static stress, and this is for the fluctuating stress. So all of the safety factors, you can find the calculation equation from the, okay, and and then this is the measures to improve vertical stress. We have studied last class the 4 factors: the stress concentration factor, size factor, surface condition factor, and the intensity factor. Okay, and and for this practice, complete the statement with the correct phrase. Which of material is chosen for evaluating the vertical stress of meshing elements? A. Yield stress sigma s. B. Endurance limit. C. Ultimate stress. D. Elastic limit. So you choose which one? You choose which one? A, B, C, D. You choose which one? A, B, C, D. Choose which? The
B.
Yes. B. Choose B. Endurance limit for evaluating the vertical stress. Okay, and point M represents the working stress of an element. If the minimal stress is constant, the endurance limit located on point A, B, C, D, M1, M2, M3, M4. So which the intersection point represent the endurance limit of the working stress M, which?
老师 M1.
M1, you should notice that the minimum stress is constant, not the stress ratio is constant. Or the mean stress is constant. The M3 is the condition. The stress ratio is constant. Okay. M1 is the mean stress is constant. But for the minimum stress is constant, we choose which one?
M2.
M2.
Yes, M2.
Yeah.
M2. when under the condition, the minimum stress is, and then it's about the contact stress. Contact stress for example, for machine gears, rolling contact bearings. We will study in the future about the contact stress. You should know that it's one of the most common methods of transmitting force in a machine. Okay, and in the chapter gears or shafts, we will start this part. Okay, and then we will say the example 2.1 in your book. Okay, an alloy shaft carrying a maximum stress. The maximum stress is 408 megapascal at critical section must operate at least the 6 power of 10 cycles at a stress ratio R is 0.25. The material has properties of sigma -1 is 480 and sigma S, the yield stress is 800 and the push sigma is 0.2. Select the critical number of cycles and it's the 7th power of 10 and the material constant M is 9. Assume the combined influence factor K sigma is 1.5. If the allowable safety factor is 1.5, determine whether the element will meet the stress requirement. So in this example, we should calculate the safety factor. Okay, calculate the safety factor, and we can say there are 2 ways to obtain the safety factor. One, the safety factor is obtained by calculation. So we can see that we first we calculate the sigma M and sigma A. Okay, sigma M and sigma A. We can use this to calculate, and then calculate the vertical stress safety factor by infinite life. By infinite life, we use this because the R is constant. R is 0.25, right? R is constant. So we use this to calculate the strength safety. Okay, let me see. There, when R is constant, we use this to calculate the safety factor. Okay, use this, and we know the values of sigma -1 and K sigma and the push sigma, and we calculate the mean stress and the stress amplitude. Then the calculate the safety factor by infinite life is 1.45, and this is less than the allowable safety factor. The allowable safety factor is 1.5. It's 1.5. Okay. And then we should consider the vertical strength by finite life. By finite life, by finite life, the stress limit, we can't use sigma -1. Okay, we should use which? We should use sigma -1n. Okay, by finite life, we use this as the stress limit. So in this equation, there is sigma minus 1 and not sigma minus 1. Any question? Okay. By finite life, we use sigma minus 1 n as vertical stress. And how to calculate the sigma minus 1 n? Because for from the stress life curve, the stage CD, we have this equation to calculate the sigma minus 1 n. And by finite life is at least the 6 power of 10 cycles, okay? And this is finite life. So we calculate the sigma minus 1 n and then calculate the safety factor. In this equation, we use sigma minus 1 n instead of sigma minus 1. And then we should consider the safety factor by static strength and use this. Okay, let me say in there we use this to calculate the static safety factor and calculate the safety factor by finite life is 1.88 is greater than the allowable safety factor. And under the static state, the safety factor is 1.67 and it's greater than the allowable safety factor. So under the two conditions, the shaft is safe. Okay, it's safe. But for infinite life, it's not safe. It's less than the allowable safety factor. Okay, this is the method to obtain safety factor by calculation. Also, you also can obtain the safety factor by using the sigma m, sigma a diagram. And here in there, draw the sigma m, sigma a diagram, and notice that, and this line AN, DN is for the finite life of material, and AD is the infinite life of material, and ANE, DNE is finite life of the element. AE, DE is infinite life of the element, and the point on A and DN, points on A and DN means the endurance stress for finite life of particle, and DNC is the stress limit for yielding. Okay, and then we can find the intersection point, and then calculate its coordination. Okay, and then calculate the safety factor. The sigma m prime and the sigma a prime, we can say for m prime. M prime is the section of line OM and the line AEDE. And this intersection point means the endurance limit by infinite life of the element for vertical. And this intersection point M double prime means the static for static strength. So there are two methods to obtain the safety factor. Usually, the first method is simple. We use the calculation to obtain the safety factor. Use these equations. So you should master this summary of the safety factors and determine which equation to calculate the safety factor. So you should consider the stress state. If it is stable stress or unstable stress, or a simple or combined stress, or it's static or alternating stress. And for alternating stress with constant amplitude, you should consider the conditions. The stress ratio is constant, or the mean stress is constant, or the minimum stress is constant. Okay. So this is all about this class. So for today, so class is over. Okay.
再见，老师。Thank you very much. Fantastic.
Okay. Okay. Bye bye. Bye bye. See you next time.
拜拜，老师，拜拜。